is I'm going to do a lot of problems today. Do a lot of applications. We learned a lot about vectors last time, and the only thing that really remains with vectors is to see many different examples of how vectors are used and manipulated. And then that hopefully sets us up for the remaining stuff. And then on Thursday, we plan on getting into basic ideas of motion. So chapter one is for the most part, chapter one is just getting down all the basics of vectors, right? So I don't have a lot of new things to teach you today. We're just going to be applying everything we've already learned. So my first slide here is an example. So right off the bat, we're going to do an example. So let's go ahead and look at this. The figure shows a car's velocity vector. Determine the speed of the car in the direction of motion. Also determine how far the car can move in 10 minutes. So the vector that's given to us, vectors are always going to be given to you in one of two forms. This particular problem gives you a format that's not generally common for vectors. We are given the components of this vector. And from the components, we're going to need to determine what the magnitude and the direction of the vector is. Okay. So generally, you're going to be given magnitude direction, where you will be told the length of the vector, and you will be told an angle. From there, you can do things. So let's go ahead and jump into this one in components. Okay. So now, the components for this vector here looks to be the x direction is -6. So this vector extends -6 meters per second in the negative x direction, so to speak. So I have a -6 meters per second. And then in y, the extent of the vector in y is 4 meters per second. So those are our components for that vector. Now, I realize that the graph here is only illustrating a single number, and the normal rules would be to go with one significant figure in this case. However, this is more of a theoretical problem as opposed to a more practical problem. And in my opinion, it's not reasonable to use one sig fig because the answers are going to be just way too general. So I'm going to make an assumption, just for the purposes of the problem, that we're going to go with 2 sig figs here. If that had to be more clear, then I'd redraw my axis here, and I'd say that these are all, like 4.0, 2.0, and things like that. But it's fine for a problem like this. All right, so to get magnitude and direction, right? So when it says scar's speed and direction, just to be clear, because this is a velocity vector, the speed to the magnitude, and the direction is going to be some angle. So the first part of that is the Pythagorean Theorem on the components. I put in my -6 and +4. We end up with radical 52, which does reduce to 2 radical 13, though you should not really leave your answer in radical form. It's just strange, especially if there's units attached to it. It wouldn't be the worst thing in the world if you did it for this problem because, again, this is not too practical. It's just kind of a general problem. But if we had a more substantial problem with, a story behind it and, things like that, you're going to want to put this out, in your calculator. So in the calculator is 7.2 meters per second. And for 2 sig figs, that's sufficient. Then we go to our direction here. And when you do your direction, you'll need to define an angle somehow. I've decided that I'm going to define my angle with respect to the negative x-axis. Having a picture with the angle specified in there is sufficient. So as long as it's clear either from a picture or from an explanation. So when I did this here, I did my based on the way I defined my angle here, I did the arctangent of Vy over Vx. Notice that Vx will need to be positive. And so the arctan of for 6 is 34 degrees when rounded to 2 sig figs. So I decided to go with that angle there. Because I have a picture, it's clear what the 34 refers to. If you did not have a picture, you'd want to say something that indicates what this is. For example, you could say 34 degrees, clockwise from the negative x-axis. That works. You could say that. It's perfectly fine. But yeah, you will need to be sort of about what that angle is. One thing I want to make sure it's extremely clear is you really don't want to specify your angle in like strict standard format, meaning the standard form of an angle from like mathematics, right? Standard form of an angle has your initial side along the positive x-axis. Then there's an angle that would be defined as something that's rotated counterclockwise from that. And if you did that here, you'd end up with what? E minus 34 or thereabouts. And that's 146. But you don't want to say 146 is your angle. It's very important that we stick with what we call reference angles. Angles that are acute and largely for convenience. It's very messy if you try to use obtuse angles. If you're trying to say something's at 146 degrees, in my experience, students don't manage that very well. Mixing up negative signs and things like that. So it's best to always keep things as reference angles and then attach negative signs to things as needed. Like for example here, when I saw that my component is negative for the x direction, so I put in a negative sign. It's something that you could get out of trig functions. For example, if I went backwards with this and I want to get a negative value for my x, I could choose an angle that's obtuse for the cosine, but just don't. I strongly recommend do not. I mean, there's only one situation I can even think of in all of the physics classes we have here where you'd actually want to use an angle that's not acute. There's like one situation where using an obtuse angle is actually a good idea. Otherwise, I don't recommend you do that. It just leads to a lot of problems. All right, so this is pretty straightforward. There was another part to the question here, and that was determine how far the car moves in 10 minutes. This is the speed 7.2. So you do want to use that. You want to multiply that by how many seconds there are in a minute, in 10 minutes, sorry. And if you notice here, I did go with my 2 radical 13 number because you don't want to use a rounded number in your calculation. You don't want to introduce any kind of rounding errors. So I did that here. And when I rounded to sig figs, I got 4.3 kilometers. So a minor little detail there, but anyway. So any questions about this problem? Anything unclear about what we did here? All right.
So 7.2 would also be the magnitude, right?
That's the speed of the car, which would be the magnitude of the velocity vector. That's correct.
Okay. Thank you.
Yep. Okay, anything else?
How were you able to determine the distance?
What?
As in, like, where do you got the 600 from the distance?
I mean, it says how far did the car move in 10 minutes, so I'm just using a simple rate times time equals distance thing. So multiplying the rate by the number of seconds will give you the number of meters. That's all I did there.
Okay.
Yeah. All right.
Wait, why did you put in kilometers?
I don't know. I just did.
Oh. Okay.
I mean, it just happened to come out to 4,300, and it seemed easier to put in kilometers. Didn't have to. Not necessary. Otherwise, it would be probably prudent in this problem to put if you don't put in kilometers, it would probably be wise to put it as 4.3 times 10 to the third meters then, just to avoid any ambiguity in the sig figs. But there's no hard rule about that. Whatever whatever is needed to communicate, the answer. I'd recommend you do this in nanometers, though. I'll say that. Don't put your answer in nanometers.
Okay.
All right.
Hey, Professor?
Yeah.
Oh, never mind. I see it now. Never mind. I get it.
Okay. All right. This other problem here is a displacement problem that uses vectors that are originally given to you in magnitude direction format. Okay, so let's go over what's happening here. Bird flies 100 meters due east from a tree. That's nice. And then it reaches the tree, and then it goes 200 meters northwest, which, whereas being specific here, does mean 45 degrees north of west. That's a little vague sometimes when somebody says northwest, but that's what we mean here. We want to know what the bird's net displacement is. So we've illustrated that in a figure here. So do notice that we have our starting point at the bottom here. Vector A represents the first part of the trip, going 100 meters due east. And then we have vector B representing the second part of the trip. Vector C is the net displacement. And the relationship between those vectors is when you add A and B up as a vector, you get vector C. So C basically tells us ultimately where the bird ends up from the starting position. So adding vectors is very common for displacement problems, and this is a great example of that. And there are a couple ways to do this problem. And I'm going to go through both ways that we're going to do the problem here. So let me jump to my solution here, which is right here. Okay, so now the first way that I'm going to do it is with trigonometry. And fortunately, since we only have two vectors in our displacement, we have the ability to apply triangle rules to solve for missing lengths, missing sides, things like that. So I'm going to do that here. I want to know what the length of C is, which would be the magnitude of the displacement, and I want to determine some kind of angle. What I'm given here is I have the length of A and the length of B, and I have one of the angles. I have the angle which is between, I guess you would call this angle C because it's opposite of side C. And so when you have a situation where you have two sides at an angle, law of cosines is a good idea. It's not the only option you have, but it's an option that would immediately get me the value for C. And so I like that. I'm going to do that. So let's go ahead and put those in here. This is the version of law of cosines that would apply. It applies to any triangle. And the way it's referenced here is I'm just simply going to say that the lengths of the triangle, right, A, B, and C with angles A, B, and C. Those are the angles that are opposite those sides. And I plug in my answers here, my numbers, sorry. A is 100, B is 200, angle C is 45. Do the magic in the calculator, and we end up with a value, I believe when rounded, it doesn't come out exact, but when rounded is 150 meters. This looks like a 2 sig fig problem to me. What do you want, doggy? I'm trying to teach. You can't hang out here. I'm sorry. All right. Dog wants to learn physics, but I won't allow it. Okay. Geez, really whimpering over there. C is 150 meters. I don't know. It's a new dog. We just got it yesterday. It's some kind of husky mix thing. Husky what? Belgian Malinois. Sounds like a drink. But I'll take a Belgian Malinois. On the rocks, whatever that means. So, yeah, we have another dog. It's a husky shepherd mix or something. And
Husky Belgian Malinois.
oh, it's a Belgian Malinois. They're both that?
Yeah, it's just that Trinity's way more
Oh, weird. Because one dog looks really pretty and the other one looks ugly as hell. So it's just crazy. Yeah, I can say it. Anyway, all right. Enough about doggies. No, it's true. One is beautiful. They have like blue eyes and they're pretty. The other one looks like just just crawled out of a dumpster. So, just kidding. I'm not just kidding. Anyway, I love dogs. Sort of. Except when they bite me and they eat everything and they take anything that's valuable to you and destroy it. That's the part about dogs I don't like. Anyway, back to vectors. Got my side, 150 meters. That's my net displacement. Now I got to know my angle. Now, what am I doing here to get my angle? Well, I have two angles specified here. I have phi, which is also known as angle B. It's the angle opposite side B. So I'm going to solve for that one, I guess. Yeah, I'm going to do law of sine. So I'm going to do the angle side pair that corresponds to C. So that's 45 degrees divided by the length of C, which, well, it's 150, but I'm going to put in the, not the rounded value. I'm going to put in whatever, it is my calculator told me it was, and solve for the angle. And we get 73 degrees, but that's actually the smaller angle out here. You can see this angle that we got, you notice, that's an acute angle. So that's not phi here, right? It's not phi here. Remember, law of sines has some ambiguous cases. When you do the inverse sine, you can get a quadrant 1 or a quadrant 4, not quadrant 4, quadrant 1 or quadrant 2 angle. And, that's why I have a picture here. Because if you did it like this and you got 73, you might go with that, but that would not be correct unless you specify that the 73 was actually this angle out here, which is theta. You could say that. But that's why the picture is really helpful in this situation. Just because, well, let me put it this way. I'm showing you this, and you're going to have a homework problem where you want to utilize law of cosines and laws of sines. But aside from this, I will very rarely invoke law of cosines and law of sines. And here's two reasons why. One, it only works for triangles. So that means you really need to have only two vectors. If you have more than that, it's a little harder to do. The second reason is this whole thing with law of sines, it can be a little tricky. There's a third reason. The third reason is students hate this. Most students don't remember their law of sines and law of cosines, and it's annoying. So you never have to do this. I'm just doing it because it's a technique that you can utilize if you like to. But let's think about a different way to do it. All right, let's go. I'm going to redo this problem through a much danker method. This is much better than law of cosines and sines. This is the component form, and this is probably how you're going to do 99% of these problems. Oh my goodness. I almost saw a bird die. That's going to be the highlight of my day. All right. So, if we do things in components, here's the beauty of components. It doesn't matter how many vectors that you have. You can have 50 vectors. And this method doesn't really get any different. So, the way you do it in this manner is you have to specify each of your vectors in component format, and then we do an algebraic sum of those, and then we reconstruct vector C. So let's go ahead and do it. Vector A would be specified as 100 I hat meters. 100 I hat meters. Okay? Angle B, not angle B, vector B. Traumatized from almost seeing the bird die, so I'm trying to recover here. Vector B is, the components would be a negative 245 I hat and a positive 200 sine 45 j hat. Now, let me walk through that a little slower. because this is an extremely important thing I just did here, and it's got to be very well understood. Now, if you remember from last lecture how we do components, okay, the way that the components are done, like for the x direction, the x component of your vector is the magnitude of the vector times a cosine or sine of an angle. Okay, so let me draw out something here to be very clear about this. Here's your angle B. You see angle B. Let's draw angle B in a thicker green. Let's do green. All right, here we go. That's vector B. And then I'm going to draw out a couple lines that correspond to its components. The x component, that's the y component there. And this is the x component. So I made a triangle, right? And the legs of the triangle are the components of the vector. For the adjacent side, 200 cosine 45. There's a negative sign there because that component does point to the left. And the left is negative. The y component points upward. It's positive. The side opposite gets a sine function. 200 sine 45 degrees, j hat. Now, I have, these are the components of vector B, written as vectors. This is the x component vector and the y component vector, and when added together, it represents the vector decomposition of B. Okay, so notice there are basically 4 parts to doing components. It's plus or minus based on direction. You have the magnitude of your vector. We have sine or cosine of the angle, and an I hat or j hat correspond to either x or y respectively. So every time you have a magnitude and direction format for a vector, and you want to do math on it, okay, like I said, the vast majority of the time you're going to want to do component format stuff. So we take our vectors that are currently in magnitude direction, we convert them to components, we do our math, and then we put the vector, any result we have, back into the magnitude direction format here. Okay, so before I move on, yes, because vector B has a magnitude of 200, so that goes in the front here, right? Taking the 40, so like, yeah, the 45, 200 cosine 45, 200 sine 45, that's determining the length of these sides from trigonometry. So, all right, now, I want to make sure it's super crystal clear to everybody here. Does anybody have a question about vector B here? Is anything unclear about what I wrote, how I'm determining that? You will see many other examples today. It's not like the only one. But for now, is there any question?
I was wondering what the I hat and j hat are for.
The I hat and j hat are unit vectors we introduced last lecture, and they just basically are attached to these numbers to tell you the proper directions. So minus I hat would mean points to the left, positive j hat means point up, things like that. Anything else? Okay, now in this particular example here, the way the angle was defined, 45 degrees, the I hat component, or the x component, got the cosine, and the j hat got the sine. That's not always going to be the case. Depending on how your angle is defined, it's possible that the I hat gets the sine function. Are you kidding me? My mom, I'm teaching. I'm teaching.
Oh, okay.
Right
bye.
now. I'm teaching.
Bye.
Okay, bye. Okay. I thought she'd get madder. Oh, well. Every time she calls me, I'm in class, I answer it. And she gets very mad at me. Why'd you answer the phone? Because I find it funny. That's why I answer the phone. Okay, anyway. All right. I'll call her back. Hope she's not going to call me and be like, I'm going to the Capitol tomorrow. What? No, don't do it. All right. Any other questions about vector B?
The way that you drew, okay, so the positive, negative at the front of it, that's
Yep.
completely wrong. How you drew the arrows, like what direction it's going.
Yeah, so this is we call this a quadrant 2 vector because it points up and to the left. And any vector that points up and to the left always has a negative x component and a positive y component.
Oh, okay, that makes sense. Thank you.
Yeah. All right, I'm going to move on here. You'll see plenty more examples of component vectors. So hopefully by the end, it'll clear up any confusion you might have.
Is that why you use the absolute value for when you use the tangent to find the actual angle?
The reason why I think you ought to use the absolute value in the tangents is to avoid any kind of confusion you might get if you do put a negative sign in. Because if you do put a negative sign in for the arctangent, you'll get a negative angle out of it, which can be a little confusing. So I think it's best to always stick with, reference angles, make everything positive. It just will be easier in the long run to think like that.
Gotcha. All right, sounds good.
Okay. So let's go ahead and do the algebra here. I'm going to add up A and B together. That requires you to add the I hat components up and the J hat components up. So they both have x components. So this is 100 minus 200 cosine 45. That ends up turning out to be around negative 41 I hat. And then there's no J hat for part A, so it's like plus 0 J hat. So it's just whatever B's component is. And that happens to be 141 J hat. Okay, so the way this looks makes a lot of sense. I mean, if you look at this, vector A had us move 100 to the right, and then the component of B that subtracts off from 100 tells us how much we had to walk back the other way. So this has got to make sense when you see it that way. Anyway, if I do the Pythagorean theorem on these components, I get the 150 meters that I got from the previous one. And if I do my arctangent, I'm deciding that I'm going to specify the angle as you see here. Okay, that's how I'm going to do that. And wait a minute, what did I do here? Oh yeah, it's for vector C. So vector C, that's this smaller triangle here. That's very tall. And so when I do the arctangent on those components, this theta is clearly the same as the theta in the picture. So that's what this refers to that theta. And I got a 72 degrees, so that works out. And so in magnitude direction before I'm at, I would specify this vector as being 150 meters at an angle of 74 degrees. And as long as I have a picture to associate the angle, I don't need to provide any additional information about the angle. If you don't have a picture, you got to specify what the reference is for the angle. I mean, there's a lot of ways you can draw a 74-degree angle. And you just got to make sure you're really clear about that. Okay.
Also, one more question. For when you define like I guess when you do A vector plus B vector is equal to C vector, you're defining its magnitude, correct?
You bet. Yep.
But the magnitude, wouldn't it be like around 100? Or at least for the I hat? Wouldn't it be like nearly like 100 or something? Oh no, it's J hat, it's I hat and J hat. Okay, never mind.
Yep. Okay. Anything else? All right. Let's keep moving. Let's keep pushing through here. Did this one. All right. So what you saw in the last example was something known as the net or resultant vector. And this is a very common thing in physics because of something known as superposition. A lot of things in physics obey superposition. One of the first ways you're going to see superposition is in the concept of forces. Forces obey superposition. And here's what I mean by that. Say you have a tug of war going on. Like, look at this picture down here. I have a coordinate system, and I have 3 different forces at different angles pulling on something. Now, these forces work independently of each other. The fact that one force exists doesn't change the magnitude direction of any other force, okay, directly. So these are independent vectors. The idea of superposition is these independent vectors can work in tandem to produce the effect of a single vector. So having these three vectors pull on something, you could create a net vector out of these three, and that would give you one single vector, and the system would behave the same as if it was being acted upon by that single vector instead of all three. That's what superposition means. This applies in a lot of other situations. For example, electric fields obey superposition. If you have multiple charges involved, the field that's established is the sum of all the individual pieces. And you'll see this in so many things. Energies like this and so many other things are like this. And so this requires us a lot of times to compute net vectors. We have to add up several of them together, right, to get a resultant vector. So let's go ahead and do this one here. This one's good. This one's so good. I'm jealous that I'm not back in college. Actually, that's not true. I'm so glad. I remember my last course very, very dearly. I remember leaving the room and thinking, never again. Never again. And then I became a teacher, so what the hell is that? I don't know what's going on with me. All right, anyway. Example 4. Seriously, though, I wish I could go back to myself and I'm like, never again. And I'm like, little do you know. Little do you know. All right, where's my notes? Okay. So I have my coordinate system placed here. I'll draw this a little bit better so you can, it's a little dark. Let's try that again. We got an X axis here. We got a Y axis here. I don't know why they drew them with arrows. I shouldn't draw them with arrows. Let me get rid of those arrows. Let's draw them with lines. Let's not get too crazy here. Line, Y axis, X axis. And I got my three vectors. Vector A, vector B, and vector C. Now these three are going to act together as if they're a single vector. And I actually drew that vector on here. Now I didn't really know ahead of time that the vector is going to look like this. But you'll see very soon that it does work out this way. So the net vector is going to be the sum of A, B, and C. Now you can't use your law of cosines and sines for this. I mean, can you do a bunch of geometric and trigonometric tricks? Yeah, but that's a big waste. I don't want to do that. Components are the way to go here. So I'm going to specify A, B, and C in component format first, then I'll add it all up. So pay very close attention to this. This relates back to what we talked about before. Uh-oh. I'm going to put that back. I'm so sorry, vectors. All right. Vector A, minus 6 sine 30 degrees I hat. So if you look at vector A, it is a second quadrant vector. It points up and to the left. The x component would be negative. The magnitude is 6. The angle that is specified here is 30 degrees. Now, look at the components here, though. Look at these components. The angle is defined with respect to the positive y-axis. So that means my y component is my adjacent side. It gets the cosine, and the x component, being the side opposite, gets the sine function. That's why this is sine 30 degrees here. It's based on how the angle was defined. So minus 6 sine 30 degrees I hat, positive 6 cosine 30 degrees j hat. That's A in component format. Okay, now, the one thing that's tricky about this one, if there's anything tricky really, is how the angle was defined. It's defined vertically. So in that case, the sines and cosines flip. But listen, you always associate with the x component, right? You always associate with I hat, whatever is along the x-axis. In this case here, it was the opposite side, okay? The y component, right? That's the adjacent side, therefore that gets the cosine. You really got to think in terms of opposite and adjacent. not necessarily in terms of x and y. Right, so likewise, B would have both components negative, and it would be negative 4 sine 45 and negative 4 cosine 45, I and j respectively. And C is a fourth quadrant vector, magnitude 3. The x component would have the cosine on it because that's the adjacent side. And then the y component is negative because it points downward. It's the side opposite. I'll draw the little component here. It goes right down. So it points down. It's the y component. It's the side opposite of the angle, so that gets a sine 30 degrees on it. And those are my three vectors. So before I move on, is anything unclear about how I determine these three vectors in their component formats? Anything unclear about that?
If you added an extra line on letter B, how would it look like? Like, you know how you add one on A to make it look like a triangle and one on C?
Yeah, I mean, if I want to specify the components for B, it would look like this. It's you basically figure out how to make a right triangle with the angle that's given. So 45's given here with respect to the negative y-axis. So the legs of my triangle, I'd have my y component go down and my x component go to the left, like that. That would be the components for that particular vector. Because you're just trying to make a right triangle with the angle that you already know. So you see all the right triangles I made here? That's how you want to go about it. Yeah.
I see them. Thank you.
Okay.
So I'm not understanding how you keep getting like for example I don't understand how you're getting these numbers for the vectors. Like, can you go over it like again?
What numbers in particular are you referring to?
Like how you keep getting the negative 4 sine 45 and then the little I thing.
It's the negatives and positives correspond to which direction the vector points. If you notice, vector A is the second quadrant vector. It would have a negative x component and a positive y component. B is quadrant 3, so they're both negative. C is quadrant 4, so x is positive, y is negative. And the way you specify these components is these, like this 6 sine 30, 6 cosine 30, these are the lengths of these are the lengths, don't call me. These are the lengths of the legs of these triangles here. The triangles correspond to the components of the vectors. So ultimately, like, you know, this 6 sine 30, let me draw it here. I'm going to draw it in what color? Let's go with blue. Let's go with the blue color. Soft blue. This 6 sine 30 corresponds to that component right there. The 6 cosine 30 corresponds to that component right there. This sine 45 is that one, and that's that one, and so on. So when I specify the vectors here, you know, the hypotenuses of the triangles, those are the vectors themselves, and then the legs of the triangle are their components. So I'm writing out those components like that.
Okay.
So every time you have a vector, you're looking to make a right triangle out of it, and then you're looking to determine the length of the sides.
So each side of this vectors is like for example, looking at the A vector, since it says A equals 6 and the n being the 30%.
Oh, n is
30 degrees here.
The n here is the unit of newtons. It's just the unit for force.
Oh, okay.
Yeah, that's just the unit. The 6 and the 30, the 3 and the 30, the 4, those are the magnitude directions.
Okay.
Yep. All right.
Thank you.
Yes. So let me clear out the stuff and let's get down to the rest of it. Now, when I go in my calculator and I punch all these in, right? So what I do is I go to my calculator and I add all of this up. Minus 6 sine 30 plus minus 4 sine 45 plus 3 cosine 30. So I'm add up all of the I hats, all the I hat components, and when I do that, I get a minus 3.23 I hat. I do the same thing for the j hats. Add all of these up, punch this in my calculator, I end up getting a 0.867 j hat. So as you can see here, based on the components of this vector, I am working with a second quadrant vector. It has a pretty long extent in I and a very short extent in j. I've approximately drawn that out here so you can get a sense of what that looks like. Now, ultimately, I am looking for the magnitude and direction. So once I have that vector, I'm going to specify an angle here with respect to the negative x-axis, sorry. And my Pythagorean theorem gives me 3.3 newtons for the magnitude. And the angle, I'm going to do, I already labeled the angle here, so it's going to be the y over the x component, and that's 15 degrees. And that certainly looks like that angle. 15 degrees is very shallow. So ultimately, my answer here is 3.3 newtons at 15 degrees. So these three vectors that were given to me in magnitude direction format, I added them together algebraically, turned them back into a resultant vector, and apparently these three vectors act together as if they're a single vector, which is this vector right down here. Okay. So, any other questions about this problem?
Just to clarify, if we're looking at vector A, the reason the I hat has sine of 30 is because the I hat is opposite from the angle, correct?
Right. The x component is opposite the 30-degree angle, right? So it gets the sine function. Exactly.
Okay. Thank you.
Yep. All right. All right. So just to be a couple things to be clear about here at this point. This first chapter is mostly devoted to vectors. So while I went on, last week, this is not a math class. Well, okay, it kind of is a math class at the moment. You're not learning any physics yet. We're learning how to use the vector mathematical tool, and then we're going to start getting into physics. So this is all just the math. This is just the math here. Okay. You're seeing little glimpses of problems that we would do, though. That's the thing. And there was something else I was going to say. Oh, yeah. All the stuff that we're doing here, that's why there's homework and other things. You need to practice this. I would be a little surprised if you just listened to me for the next hour and 20 minutes and were like, yeah, this makes sense. I get this. It's totally fine. No, you'll be practicing it and going through problems, and I'll give you plenty. So let's keep moving on to another problem, which is this problem right here. All right, here's another kind of problem. Very, very, very similar to net vector. This one, however, is what's known as equilibrium. And it's a subset of net vector problems. It's net vector problems where the net is 0. So you sum the vectors up and they equal 0. So very similar situation here. What's nice about equilibrium problems is you can have several vectors involved with an unknown vector. And as long as you know or you want the system to be in equilibrium, you can solve for it. So if this is my problem here, where I have a 3 unit of force vector to the right, this other one is up and to the left, and then I have this unknown vector that points down and to the left. If this is supposed to be in equilibrium, then vector 1, vector 2, and vector 3 should all sum to 0. And so you can't algebraically manipulate this to find that vector 3 must be the opposite of the sum of 1 and 2. That just comes from the algebra here, which you can just subtract the vectors from both sides of the equation, and so on and so on. So let's go ahead and do this problem. All right, let's go ahead and do it. Let's jump right into that one. Okay. So given the two vectors, I want to find a third vector that puts the system in equilibrium. So again, I'm going to label these vectors A, B, and C, according to the picture here. I add them up. That I want that to be equal to 0. That means vector C is going to have to be the opposite of A plus B. Well, I got to specify what A and B are. Now, I don't have a coordinate system here, but as you can see, it's very easy to place down a coordinate system here, which I'll do. That's terrible. Let me try that again. I'm trying here. Let's see. How about this one? Draw. That's not bad. Ooh, look at that. Sharp. All right, there's my coordinate system. And vector A, as you can see, would simply be 3 I hat. I'm going to suppress any units here, just as units of force. I don't care what that is right now. So just 3 I hat. And then, oh, shoot. All right, I got to get that later. Okay. Vector B, well, I've decided to specify an angle with respect to the negative x-axis here. So while they give me 120 here, I'm going to be utilizing the 60-degree angle on the other side, because I like to work with acute angles only, and then put in negative signs when appropriate. So vector B is negative 5 cosine 60, right? Negative because it points to the left. 5 is the magnitude. Cosine, well, that's the adjacent side, which is the x direction. That's I hat, so that's good. The y component is 5 sine 60 j hat. Again, 5 for the magnitude. It points upward, so it's positive. It's the side opposite. I will draw for you here what those components will look like. Right? You're making a triangle. So here's the x component here, and here's the y component there. So x component goes left, y component goes up. That's my triangle, and the components represent the sides of that triangle. So 5 sine 60 is that vector. Okay. All right, so I'm going to go ahead and add those two vectors together. So I'm going to add together the I hat stuff and the j stuff together. So it's going to be 3 minus 5 cosine 60 when I add up the I hat stuff. J hat's 5. There's no j hat component for A. So I add up all those, stick that negative sign in front, and I happen to end up with a negative 0.5 I hat and a negative 4.33 j hat. So having both components negative means I definitely have a quadrant 3 vector that happens to go down quite a bit and not so far over. So this vector here is kind of right. I mean, it's not quite to scale, but whatever. It's fine. Anyway, so let's go ahead and do the components. The magnitude here. We do the Pythagorean Theorem on the components. We get a 4.4. We do an arctangent. Make sure you specify your angle. I'm specifying with respect to the negative y-axis, but in quadrant 3. And it turns out that's an 83-degree angle. That makes sense if you draw that out. So the angle, vector C, would have to be 4.4 at 83-degree angle as drawn, and that would put the system in equilibrium. Okay, so very similar problem, not too different. The only thing extra here really is, well, you have to visualize the coordinate system. It's always good to put the origin at the center of this thing, and then for equilibrium, you have to specify what that third vector is going to be. All right, any questions about this one?
I have a question.
Yes.
Why do you use cosine and sine for vector B but not for vector A?
Well, vector A doesn't have any components to it, really, other than the I hat component. Vector A is parallel to the positive x-axis. So there's no angle, basically. If you want to speak of any angle, the angle is simply 0. Now, vector B, on the other hand, does have components to it, right? It has, again, let me draw things out here. Let's do that and do this. So if I were to draw, again, the coordinate system out here, you can see that A only has an x component, and it's just 3 I hat, whereas B has an angle. If A had an angle, we do the same thing, but it doesn't.
Okay, thank you.
You bet.
Professor, for B, you have negative 5 cosine 60 degrees. Could you use 30 degrees too?
You can. 30 degrees would be the angle with respect to the vertical axis, but if you use 30, then your I hat should have a sine 30 on it, and the j hat stuff should have a cosine 30 on it, because now the references have switched because you're using a different angle now.
Okay, thank you.
Yeah, you could see that does work, right? Because cosine 60 and sine 30 are the same. And sine 60 and cosine 30, they're the same. So you can see how that works out. That works just fine. Okay. Any other questions? All right, fantastic. Let's keep going. 20 minutes. What do I got left here? That, and that. Easy. Well, not the stuff's not easy. Only 3 slides left is easy. All right. So, well, here's the thing. We like this stuff so much that we want to go a little wild with this now. You know, everything we did is, you know, X and Y coordinate systems. You know what? Let's tilt that coordinate system. Let's go crazy and let's tilt our coordinate systems and let's do some other stuff. Now you're thinking, what the hell? Don't do that. Don't tilt your coordinate system. It's hard enough. And I'm telling you, listen, there are a lot of situations where we're solving problems where there are things at an angle. For example, a box that slides down an incline, which there's going to be so many boxes sliding down inclines in this class, you're going to be wondering what the hell, you're trying to get a job at a warehouse or something here. There's a lot of boxes down incline problems. Anyway, my point of that is that the vast majority of forces and vectors relating to speed and acceleration, they're not on your standard XY coordinate system, in the sense that y represents horizontal and x represents horizontal and y represents vertical. You actually have to have a coordinate system that is tilted so that more of the vectors lie on a coordinate axis than not, and it will make the mathematics easier for you. The issue is that it looks strange. And that's really what you should tell yourself. Like, when I do tilted coordinates problems, the reason why they seem hard is because they just look different. Once you see through that, you realize that they're no different than the problems we normally do. It just looks strange. What this is required for you to do, though, is we don't want to talk so much about X and Y, although we will. You really have to think about things in terms of parallel and perpendicular. Okay? So, for example, if this was a slope, the x-axis probably represents a parallel to the surface, and y is perpendicular to the surface, or something like that. And that's how you'd want to think about those things. All right, let's do a couple problems. All right, so a pine cone falls from a pine tree growing on a 20-degree slope. So we see a slope here. We got our pine tree. We got a pine cone that falls straight down. Now, I've drawn that vector right here, and I'm also going to draw on here a couple other vectors, because this vector here is defined, you know, just straight down, right? That's standard y. But I want to know the speed of the object with respect to the tilt, to the slope here, because there are going to be problems later that I'd want to do that with. So let me make sure it's really clear. I'm going to draw out those components here. Okay, so if this is our vector going straight down, I can draw out components. Here's one component here. I'll draw it a little thicker, actually. So this would be considered the perpendicular component, and it happens to go with y. And this one is the, right here, this is the component that is parallel to the surface, and that would be x. So there's my triangle. And so if I want to specify the parallel and perpendicular components, the parallel, which is given by the double lines here, the v double line, is the magnitude of the vector, which is 10 degrees, sorry, not 10 degrees, 10 meters per second, times the sine of the angle, which the angle happens to be 20 degrees here. It does so turn out that the slope angle is the same as the angle that's drawn here. So minus 10 sine 20 degrees. It's minus because this is pointing down the negative axis, and I've decided to call this left-hand side negative. I didn't have to do that, but I did. That's standard, so I'll do that. And similar thing with the perpendicular component, minus 10 cosine 20. And I punch those in my calculator and I get negative 3.4 and negative 9.4. So yes, this thing drops straight down at 10 meters per second, but if you want to break this up into what is its speed relative to a parallel and perpendicular direction to the ground, we would tilt our coordinate system and we would do it like this. Okay. Yeah, just right there. Thanks. Okay, let me jump into one last problem here. This involves everything, this last problem. We got everything going on here. All right, so, in fact, let me jump back to the slide just so you can see it without cluttered. Okay, so here's what we're dealing with here. We have a situation where we have 3 force vectors, and they're being applied to an object that is on a 30-degree incline. Now, as you see here, 2 of the vectors run either parallel or perpendicular to the surface. Only one vector goes straight down. So this is a situation where we'd want to use a tilted coordinate system because there's more vectors along the axis than not, and it will make the mathematics easier. Because if I have a tilted coordinate system, F3 is the only vector with components. So that's going to be easier for us. All right, so the net vector is going to be vector 1, vector 2, plus vector 3. The coordinate system is drawn tilted, and the one thing you have to take note of is the angle of the ramp here, or the angle of the incline, 30 degrees, is the same as the 30 angle that you see right here. The y-axis and vector 3 also make 30 degrees. Those are similar triangles there. F1 is minus 3 I hat. F2 is 6 j hat. And then as I mentioned, F3 is the only vector with an angle with respect to the tilted coordinate system. That is a quadrant 4 angle. So it has a positive x component, 5 sine 30. Sine 30 is the opposite side, which is parallel with x. Minus 5 cosine 30, minus because we're pointing in the negative y direction. Cosine because the y component is the adjacent side of the 30-degree angle. That goes with cosine. That goes with j hat. Add up all the I hats, all the j hats together. I get the numbers that you see down here. And then, as always, Pythagorean Theorem for the magnitude and the angle. Now, it turns out that this vector right here is quadrant 2 because it has a negative x component and a positive y component. So I drew a little theta right there to represent the angle. And so my arctangent is going to be the y over the x component, make everything positive, and I get a 73-degree angle here, which is a lot than this looks, but that's how it works out, I guess.